All right, in today's notes, we're going to look at piecewise functions, how to graph them, how to evaluate them, how to write their equations. And we'll start by reviewing first how to graph lines. So lines, at least for today's example, will take this form. This form is called slope-intercept form, something you're familiar with, y equals mx plus b, where m is the number being multiplied in front of the x, so m times x. So this number is m, and that is the slope of the line. It is best to think of slope as a fraction, rise over run, change in y over change in x, where the numerator of this fraction is how far up or how far down, depending on whether or not it's positive or negative, and the denominator of the fraction is how far to the right. So the rise can be up or down depending on positive or negative, but the run is always to the right. Okay? So if we think of slope as a fraction, rise over run, and remember whole numbers can be written as fractions all the time if you put them over 1. So for example, as we'll see in a second, this can be thought of as 3 over 1. And the b is the y-intercept, the y value where it crosses the y-axis. Okay? So let's graph this very quickly. Y equals 3x plus 2. This is a pretty easy line to graph. It has a y-intercept of 2, so it will cross the y-axis at positive 2. And it has a slope of 3. So the slope here is 3, although we will, again, it's probably best to think of this as a fraction, so 3 over run. Wow, Freudian. 3 over 1, where the rise in this case is positive 3 and the run is 1. So from this y-intercept of 2, I can follow these directions, which is to go up 3, rise 3, so 1, 2, 3, right 1, and I'll get another point that's on my line. And I could continue this for as long as I wanted to. You go up 3, right 1, up 3, right 1, and we could kind of go on that track forever. Similarly, if I go up 3, right 1 to get here, I can kind of track it backwards and go left 1, down 3, left 1, down 1, 2, 3. And we could continue that in both directions, and then we would have this line. Y equals 3x plus 2 is the line that crosses the y-axis at 2 and has a slope of 3. Okay? So that's how you graph lines, generally pretty easy. Let's graph this line, but kind of add one extra piece to this process that's going to help us in our lesson for the day. So we could graph this line. It'd be pretty easy to graph, where m in this case is going to be negative 2, and b in this case is negative 3. Okay, so we know the slope, we know the y-intercept, and we could graph this line. But let's say I add a domain restriction. So let's say I add a little statement that says only when x is less than or equal to 1. So normally we would graph lines that are kind of infinitely wide, and they extend from positive infinity to negative, or from negative infinity to positive infinity. So they have a domain of all real numbers. So they're going to be infinitely wide left and right. This restriction here says, okay, you can graph this function, but only for values of x that are less than or equal to positive 1. So let's think what that should mean. First of all, where is positive 1 on the x-axis? Let's say that's here. Then let's try to graph negative 2x minus 3, but under this domain restriction. So we're going to graph negative 2x minus 3, but we're only allowed to graph it for x values that are less than 1. So here's 1. Less than 1 is everything to the left of 1. Okay? So let's think about what this would look like. It would have a y-intercept at negative 3. And it would have a slope of negative 2, or if you want, negative 2 over 1. So remember, rise over run, down 2, always to the right 1. Okay, so down 2, right 1. Down 2, right 1. We could track it backwards. Instead of down 2, right 1, we could go up 2, left 1. Get here, and continue that process for as long as we wanted to. And we would get a line that looks something like this. Okay. Now, I could, if I wanted to, graph this whole line, and it would continue on in this manner, like so. But per our restriction, we're only allowed to graph the function negative 2x minus 3 for the x values that are less than or equal to 1. So all of the stuff that isn't less than 1, that is, all the stuff that's greater than 1, is not included in our graph. Okay? So we're not going to graph this whole thing. We're only going to include the portion of this graph that satisfies this condition, so that is less than 1. So I found 1 on the x-axis. I kept all the stuff that's less than 1 or to the left of 1. Everything that wasn't less than 1, I have chosen to ignore. Okay? So this is the graph of this function with this restriction. Okay? A question is, a lot of the time, what happens at 1? Well, that's going to depend on whether or not this or equal is here. You probably remember that because the or equal is included, I could put that closed circle there. If it was strictly less than 1, I would have to put a open circle around that point. Okay. So let's, now that we've kind of reviewed a few things, let's actually look at our examples. In example 1, it looks like we have a piecewise function. Now, a piecewise function is a function where we have stitched kind of several things together to form a single function. So, for example, the following picture is not a piecewise function because key word here, piecewise function, if I asked you, is this picture a function, I hope all of you would say no, because this fails the vertical line test. If you drew a vertical line through anywhere on this function, it's going to pass through more than one spot. And remember, if it's a function, it can only cross through once. So this is not a function. But the following picture is a function. For example, I could take that same quadratic, but I could cut it off at a certain point. And I could just keep the stuff to the left. And I could take this same line, but I could cut it off at a certain point, right? This is what we call a piecewise function. It's got kind of a quadratic piece, and then at some x value, maybe x equals 2, I don't know, at some x value, it stops being a quadratic and starts being a different function, this line. Okay? So this would be an example of a piecewise function. I'll say this would not be an example of a piecewise function. And you probably see that this would fail the vertical line test here. So it's very important that at those moments where it transitions from one function into another, that one of them or both of them have an open circle. They can't both be closed because that's a failure of the vertical line test and thus not a function. Okay? So this is kind of what we're talking about when we say piecewise functions. We're talking about these images that have several pieces kind of stitched together to form a single function. All right, so let's graph this piecewise function. This graph looks like it has two pieces. There's the top piece, 2x plus 1. We could probably graph that line. There's the bottom piece, 2x plus 2. We could probably graph that line. But then there's these restrictions. The graph of 2x plus 1 is perfectly fine as long as x is less than 0. The graph of 2x plus 2 is perfectly fine as long as x is greater than or equal to 0. So we've got these two functions with two restrictions, and we're going to make sure that we satisfy both of the rules here. So let's start with the top one, 2x plus 1. So I'm going to imagine what that line's going to look like. That would have a y-intercept here at 1, and would have a slope of up to right 1, up to right 1. But it's only allowed to, I'm only allowed to graph 2x plus 1 when x is less than 0. So here x is 0. All the stuff that's less than 0, if I use that slope of up to right 1 or backwards left 1 down 2, we would get this graph. Okay? Normally, the line 2x plus 1 would continue on forever. having a y-intercept of 1 and a slope of up 2, right 1, up 2, right 1, up 2, right 1, forever. But because of the restriction here, x is strictly less than 0, so you could probably imagine why I put that open circle here because of that less than sign. So we just kept the stuff that was less than 0. X is less than 0. Okay? So we have satisfied the first piece of this function. Now let's look at the second piece. 2x plus 2, but only when x is greater than 0. So here x is 0. All the stuff greater than 0 is to the right of 0. So we're going to graph 2x plus 2, which has a y-intercept of 2 and a slope of 2. And it would look like that. Again, normally we would continue that function forever left and right. But because of the restriction, we're only graphing 2x plus 2 when x is greater than or equal to 0. And because of that or equal sign, we put that closed circle. And there's our function. It satisfies the vertical line test everywhere, including 0 because of the open circle here. And so we have a nice function. Let's evaluate this function. Let's find f of 3. Because we have a graph, we could just find when x is 3, 1, 2, 3, y is what? So when x is 3, y is 1, 2, 3, 4, 5, 6, 7, 8. It looks like when x is 3, y is 8. And we have that. Okay, so that's not too bad, but what if you didn't have the graph in front of you? And we're going to do the rest of these problems on this page. We're going to evaluate, but we're going to evaluate by not looking at the graph. Okay? So we could have still found 8, but how? Just looking at this. Well, how do you find f of 3 when you're given an equation? Hopefully you remember that you find f of 3 by plugging in a 3 in for x. So that's pretty easy, but now the question is, which one? We have graphed both our pieces, but which one? Do I plug in a 3 into the top one? Or do I plug in a 3 into the bottom one? Because I'm only allowed to plug it into one. If I plug it into both, I could get 2 different answers, and that's a problem. So I want to make sure that when I plug in that x value of 3, I pick the right function to plug it into. But how will I know the right function to plug it into? And that is where these restrictions come into play. When x is 3, I want to make sure that the function I plug 3 into has the right restriction for it. So let's look. When x is 3, so when x is 3, is 3 less than 0? Is 3 less than 0? And the answer is no. 3 is not less than 0. When x is 3, is 3 greater than or equal to 0? And the answer to that is yes. So the second equation is the one I'll plug this into. And when I do, what's 2 times 3? 6. Plus 2 is 8. Okay? So still pretty easy. We're still, when we talk about piecewise evaluations, we're still plugging in that number in for x, but we're making sure that we look at these restrictions and pick the right one. Okay? Let's look at f of 0, now that I've completely colored all over this. But f of 0, so when x is 0, this is our x now, when x is 0, which of these inequalities is satisfied? Is the top one satisfied? And I hope you agree no. 0 is not less than 0. That's not true. 0 is 0. 0 is not less than 0. If we look at the second inequality, 0 is greater than or equal to 0. Specifically equal, right? 0 is greater than or equal to 0. So the second one is the one I would plug it into. 2 times 0 is 0, plus 2 is 2. Right? And you can tell by looking, when x is 0, y is 2. Finally, negative 3. When x is negative 3, the top one is satisfied. Negative 3 is less than 0. Please be careful with your negative sign. Negative 3 is less than 0, to the left of 0. So I would plug it into the top one. 2 times negative 3 is negative 6, plus 1, negative 5. And you can see here, when x is negative 1, 2, 3, y is negative 5. Awesome. So let's start example 2. We'll do example 2 and then we'll finish the video. Let's start example 2 by doing these evaluations, so without the picture. What's f of 6? Well, I know that x is 6 in this case, so I'm going to plug it into the right one. I just got to test which one of these inequalities is satisfied when x is 6. The bottom one is not, right? 6 is not less than or equal to 1, so that one is out. But the top one is. 6 is greater than 1. 6 is greater than 1. So the top one is the one I would plug the 6 into. What is 6 squared plus 2? 6 squared is 36 plus 2 is 38. Right? 38. So you can see already why sometimes having the graph in front of you isn't all that helpful, because when x is 6, y is 38. That's way off the graph, and so we may not see that sometimes. So that's why it's helpful to know how to do it from just the equation. Okay, what about when x is 1? Okay, is 1 greater than 1? No. Is 1 less than or equal to 1? And the answer is yes. 1 is less than or equal to 1, so the second equation is the one that I will plug the 1 into. So plugging in a 1 in for x, that's negative 1 plus 1. Negative 1 plus 1 is 0. Negative 1 plus 1 is 0. So when x is 1, y is 0. And then finally, when x is negative 1, negative 1 is not greater than 1. Negative 1 is less than or equal to 1. So I would plug that in here. Be careful, though. If you plug in a negative 1 in for x, that's negative negative 1 plus 1. Negative negative 1 plus 1. Now, negative negative 1 is just 1 plus 1 is 2. So we have those. Okay, so let's look at how we would graph this thing. Maybe we start with the top one there. It says x squared plus 2. Well, we haven't talked about it in this video, but x squared plus 2 is just your standard quadratic that goes through the origin, but shifted up 2. So x squared plus 2 is a pretty easy graph. X squared plus 2. So we know what that looks like. But we're only allowed to graph it for when x is greater than 1. So normally, it would cross through here at 2, right? And go right 1, up 1, crossing through this point. And right 2, up 1, 2, 3, 4, crossing through this point. And so it might look something like this. That's kind of tough to see what I've done there, but I did it in my head, but there's nothing wrong with doing it on your own, and even if you had pencil, you could draw it in and then erase the section that matters, but because I'm doing it in pen, I did it like this. But maybe as you're practicing these, you would have, I'll do it in pencil so you can practice, you would have drawn x squared. Of course my pencil sucks. Dang it. I'm doing it in pen, y'all. X squared plus 2, so this is x squared plus 2, right? You should have probably known that, x squared plus 2. But we just kept the stuff that satisfies this inequality. So all the stuff where x is greater than 1, we keep. All the stuff that doesn't satisfy this, we ignore. So here's x being 1. So all the stuff that is greater than that, or to the right of that, I kept. So all of this good stuff is on my graph. That's how I got this piece. All of the stuff over here that doesn't satisfy this, we ignored. So I didn't even draw that over here, right? And why did I put the open circle? Because of the value here, okay? So that's how we got this section here. All right, negative x plus 1, that's a line with a y-intercept of 1 and a slope of negative 1, so down 1, right 1, down 1, right 1, forever, and then kind of tracing things backwards, we would get this here. Why did I stop at 1 and not continue going? Well, you guessed it. I'm only graphing negative x plus 1 for when x is less than or equal to 1. So, again, normally that graph would look like this forever. but we found where x was 1, and we just kept the stuff that was less than 1. So that's all of this good stuff. Everything that was bigger than 1, we ignored and did not include in our graph. Okay? So that's how I got this section and this section kind of stitched together into a single graph. Real quick, let's check some things. When x is 1, is y 0? When x is 1, y is 0. Okay, that checks out. What about when x is negative 1, is y 2? When x is negative 1, y is... Oh, that checks out too. Cool.